And I guess the next thing I should mention is, in case you missed my announcement that I sent out, finally I posted the remainder of the first test. The last 40 points of the first test is open on Moodle. It will be open until Monday, whatever day Monday is. Today is what, the 21, today, what day is today? So it'll be up until the 28th at 11:30. So please complete the remaining 40 points of the test by Monday at 11:30. So you might not want to start at 11 to do that on Monday. You might want to get going on it a little bit before that. Okay, so what that also means is we had finally, took me a long time because I like to blather, and I'll probably blather on these slides as well, but that's the way I work. I posted a new set of lecture slides, lecture 3. That's where we will begin our new unit for test 2. You know what I think I'm going to do, since I'm in such a great mood? I'm going to do the same thing I did before. I'm probably going to break the test 2 up into segments, unless anybody wants it any different. Probably I'll do the same thing like I did before. I'll probably give us a little bit incentive points to get started, and then I'll put points based on the things we talk about for you to complete on Moodle. So it'll be pretty much the same as format that we've already seen for test 1. Why not? That seemed to go okay, I guess. All right, so in any event, where we're going to head now is to look again at how charge affects matter. So we're going to, we've now kind of broken down the nature of matter to the atomic level. Eventually, we're going to put matter together in combinations to make molecules. But before we do that, let's talk about how elemental forms of matter are conductors of electricity. So a lot of the discussion we're going to have here is about the conduction of electricity by the elements themselves. A large number of the elements are conductors of electricity. And as a matter of fact, we have a specific name that we give to the elements which are conductors of electricity, and that is that we call them a metal. Now, I'm sure everybody here knows the term metal. One of the properties that is required to be in the metal club is that you're a conductor of electricity. There are other properties that go into being a metal, and they're really not as important as this one about conducting of electricity. But probably you would, if I was going to ask you generally what you thought maybe some properties of metals would be, the first one you would probably come up with is that they're solids. Metals are solids. Well, you know what? That's interesting that we think that way, but to a chemist, not all metals are solids. And the most notable non-solid metal is mercury. As weird as that sounds, we have liquid metals as well as solid metals. As a point of interest, another of the rules to be in the metal club is that when you combine with other elements, you like to be an electron giver. You like to donate electrons to other things. Turns out that that's what metals love to do when they start combining with other elements to make compounds and molecules. We're going to delve into that idea of combining atoms together later. Right now, let's just talk a little bit about metals in the elemental form, and we'll talk about the properties of their conduction in the elemental form. So I have a whole bunch of slides on the properties of electricity in matter, and we're going to have to do a little bit of background discussion before we can get to the point or get specific about particular metals in the table and their individual behaviors. So what I'm going to do is, as I usually do, I'm going to pop my slides up here and do a presentation to the class of my PowerPoint. So I'm going to, like I always do, I'm going to flounder around for a minute here with sharing my screen. So I'm now hopefully getting to the point where my screen will be shared. I'm presenting to everyone, it says, and I'm going to present my PowerPoints, and then I'm going to start my slideshow, and hopefully all this will go smoothly. So as we now delve into a discussion of charge in matter and the behavior of charge in matter, I want to first talk about something called a vector quantity. Now, I wouldn't be surprised if you took 101 previous to this, that you had some discussion about a vector quantity, maybe not. Vector quantities are pretty cool. So we're going to start off by describing the mathematical description of force in nature, because electrical charges interacting with each other impart force on one another. And to describe the way in which force is imparted from one bit of matter to another with electric charge involved, you have to use the concept of a vector. And again, probably you mentioned these things if you took 101, but we're going to say some things about them here. I'm showing this guy, J. Willard Gibbs, because he's the person who came up with the concept of the vector. And maybe I say that at the bottom there. He introduced this idea of vectors into mathematics for describing the behavior, the unique behavior that things like this have. Now, as I like to do, let me just spend a minute just to say a word or two, give a little human interest background about this J. Willard Gibbs. I'm sure you never heard of him. But I will tell you what, he was one of, if not the, he was one of the greatest American scientists of all time. Without question, there's no doubt about that. If you really want to know my thought on this, there's really not a whole lot of truly great American scientists that contributed to the foundations of science. Most of it was European, without question. All the greats came from Europe who did the contributions of the foundations of science. A lot of them, of course, from England, but many from France, Germany, and even Italy. Lots of people contributed to what we know. But he was one of the great American scientists. He actually was a professor at Yale University. Yale was open a long time ago. He was a professor at Yale. And believe me, the work he did was underappreciated by the scientific community in general, because they didn't think anything good could come from America in the early 1800s. So nobody really paid close attention to what he was doing. But again, a Yale University professor who came up with this idea of the vector. He also made incredible contributions in the science of thermodynamics, which is energy study, which we'll talk about later in our time together. I'm sure his name will come up again when we talk about thermodynamics and the study of energy transfer between bodies. So we'll bring him back up at that time. And he, as I said, he's one of my heroes in science. So what is a vector quantity? And again, if you took 101, you might have talked about these. This is a quantity that has two important features or components that we have to monitor. A vector has a magnitude or an amount. And this is just like any other numeric measurement we've been talking about so far. Science is based on numbers, and you have to make a measurement of a number to get a scientific quantity. So a vector has a number value associated with it. But equally important to the number value associated with a vector also includes a direction. And what we will deem those directions to be is quite simply either a push or a pull. And I think you get the connotation of what I mean. I can push with a certain force, but if I pull with a certain force, it's going to do something completely differently. And that's the key feature of the idea of the vector. Not only is there a magnitude or an oomph behind my action, There's a direction associated with my action that has to be accounted for to fully describe the situation. Okay, so what are some common vector quantities? Let me tell you, there's a lot more than you probably think. The first of all is position or displacement, if you like to call it that. A lot of people call this displacement. I'm just going to call it where you are. Where you are is a vector quantity. For instance, somebody asks me, well, where are you located? And I say that I'm 40 miles from New Orleans. Well, guess what? If I tell them 40 miles from New Orleans and they set out to find me, they might have a hard time finding me. Why? Because I have to be very specific about what direction you must travel 40 miles from New Orleans to get to me. Literally, you could end up in an infinite number of places other than where I am, including not only the circle of Earth that you can walk across, you could go 40 miles upward in a wide variety of directions. You could go 40 miles downward into the Earth in a wide variety of directions. And unless I specify not only this number quantity describing where I am, but also the position, the direction that you should take to head with that distance, you're not going to find me. Okay, now anything that's associated with distance then almost automatically becomes a vector. Like what? Like velocity. Velocity is change in distance. Now, it's change in distance with time, of course, sorry. So I look at how far I go, and I divide that by how long it took me to go that distance, and I have my velocity. And again, I will offer the same thing. If I'm going 40 miles per hour, I could get from New Orleans to where I am in 1 hour. But again, the velocity vector that I take not only has to have a magnitude of 40 miles per hour to get me to the location of here from there in 1 hour, I have to make sure I'm also traveling with that velocity in the proper orientation, or I will not get to this position. Okay, now there's a competing quantity that your mom and them would use as a synonym to velocity, and that would be speed. But speed has a specific connotation. Speed is the magnitude of the velocity. It's what number quantity is associated with your change in position with time. To specify velocity, you not only need speed, you need direction. Now, the thing in your car is properly named. It is the speedometer. It tells you what magnitude of velocity you are moving at. However, it doesn't tell you what direction you're moving at. Actually, nowadays, we're kind of getting more like a vector quantity. How? You look up in your mirror, if you got a fancy car like me, and in the corner of my mirror, it's got an N or an NE or a W or a SW telling me what direction I'm going in. So I'm kind of getting the velocity information by looking at the magnitude from the speedometer and looking in my mirror to see the direction. So again, speed is a component of velocity, but it is not the true whole story of velocity unless you add the direction that you're taking that magnitude of speed with. Okay, now since you can stop and start and change your speed, you can also then accelerate. Acceleration is changing velocity. And again, acceleration has a direction. It has an indication of which way you are changing that speed. And then what's some other very important ones? Force. A push or a pull on an object is a force. And notice I've basically specified direction by naming it two names, either pushing or pulling. I can push or pull with the same magnitude, meaning give it the same oomph of push and the same oomph of pull, but these are going to occur in opposite directions of one another. And now this is covered up with my little stupid little thing that says you want to quit presenting, but what else we are going to recognize is very importantly characterized as a vector is what we will call a field. And the field I've already mentioned a little bit, and we'll talk a little bit more about today. It's push or pull, but it's push or pull at a distance. It's push or pull without touching something. You and I can't exert a field. You or I must be contacted to an object to exert a force on it. Same thing is true with a bulldozer or an automobile. An automobile cannot exert force and accelerate you unless you're touching the automobile. When I push on the gas, the seat pushes my back and changes my velocity down the road. But unless I'm touching the seat, I will not be accelerated by the car. So any machinery that we use is what we call exerting contact forces. It must touch the object in order to push or pull it. Other weird things in nature, though, don't have to touch an object to push or pull it, including the planet Earth. The planet Earth can push or pull you. Typically, we call it pulling you, and we'll talk a little bit more about that later. It doesn't push us, but it does pull us. And when it pulls us in a direction that is specified by compared to where the planet Earth certainly is. Now, charges also, electric or magnetic interactions are also going to be able to do action upon you without touching you. So action without touching you, again, we're going to call a field. Okay, now to contrast a vector quantity in physics, we also describe a scalar quantity. These are quantities that have a magnitude and a sign, and sometimes the sign is telling you something about direction. I'll point that out in a moment. But there's really not necessarily a direction to it. Now, what's some common scalars? Mass, or how much you weigh. Really, that there is a slight difference between mass and weight, but we'll use them interchangeably for what we want to do. You don't have a direction to how much you weigh. It's just a number value. Time does not have a direction associated with it. Now, if we could go forward or backwards in time, I guess we might have to do something like that. But as far as we understand, time is scalar. What else do we have listed here? Temperature. Temperature is a value that doesn't really have direction associated with it. Volume, energy, and voltage. All these things are just numbers. That's why, as a matter of fact, we're going to spend a little bit of time talking energy in our next unit. But when we notice one of the important aspects of energy is that you don't need to specify a direction. In some regards, that makes it easier to work with than working with force, pushing or pulling objects around. Okay, so scalars can be added and subtracted and multiplied or divided by normal rules of arithmetic, but vectors can't. So you got to be a little tricky when you combine vectors. And what I would mean to show you an example of that, say you run out of gas in your car and you and two of your buddies are in the car and you've had a couple drinks, which you shouldn't drive, okay, but you had a couple drinks, and now so you're going to get out and try to push your car. Well, guess what? This is a vector action, you and your buddies pushing your car. So if one of you remains in the car to steer it, and the other two get behind the trunk, then their combined action will exert more push on the car than their individual actions. So there's a way in which their vector actions can be combined. But what if one of your buddies goes to the front of the car and your other buddy goes to the trunk of the car and they start pushing equally from the front and the back? Well, now their vector actions are in opposition, And even though they're pushing with the same magnitude, they have canceling directions. So there's no net force on the car. And if there's no net force, there's no acceleration of the car. So it's important that you, when working with vector quantities, that not only do you concern yourself with the oomph of the vector quantity, but also with the direction of it. Now, again, I'm to those of you out there who already spent a great deal of time talking about this, maybe last semester, fine, I'm sorry, but this is going to be important relative to when we start to look at charged matter later in the period. So I'm just throwing these things out there as a review to the idea of this important quantity that we call the vector quantity. Okay, so how are we going to represent vectors, and how do you see them represented in scientific literature? Now, we're not going to have much need to do such things. I just thought I would show you these representations in case you run across them somewhere where you're reading something and you don't quite understand what is being implied by what you see. Well, when you're representing vectors, we often either use boldface type, but certainly that can be misleading because we use boldface type a lot when we're just trying to emphasize things, and it might not necessarily mean it's a vector. Certainly, if you put a little hat on top of the letter representing the quantity, and the hat is an arrow. So when you put an arrow hat on top of a quantity representing a value, then you know not only is there a number associated with that value, there is a direction associated with that value. And to completely describe a situation, you better have both quantities. Okay, so here's just some examples of positions on a Cartesian scale, x, y, z, or a radial distance r. Acceleration vector could be written with an A with a little hat on it, and things of that sort. Now, things that we're going to be using a little bit later will be things like the electric field, the push and pull that a charge will exert on other matter. So that's where we're heading. Here's an example of a velocity. So this part is not that important because we're not going to really do a lot with the numbers of it. If you're talking about the magnitude only, usually you put the vector in brackets, and then that means that it's just a number value representing only how much force you're applying or what speed. The bottom one that I'm showing on the bottom left would be the speed. The V in brackets is the magnitude of the velocity, and the magnitude of the velocity is the speed. Okay, so let's note, and this is, again, it goes back to Gibbs. This was the important one of the important contributions he made with vectors, but he made many other very important contributions. A very simple pictorial representation of a vector is done with an arrow. So if we use an arrow to represent it, here's what you do. Of course, you put the tip of the arrow pointing in the direction of action. Not too difficult to imagine. So importantly also is the length of the arrow. The arrow is drawn proportionally in length to the scalar or magnitude of the action. So if it's a velocity vector, if you have two velocity vectors and one is 1 inch long and the other is 3 inches long, then you know number one is going at 1/3 the speed. That's number two. The 3 inch long vector is representing 3 times the speed of the 1 inch long vector. So that's kind of combining the actions of magnitude and direction into a pictorial representation. So for instance, if this is a vector describing a push of F1, and this is a vector describing a push of F2, notice these pushes are acting together. And then quite simply, I can combine the two vectors. If I measured the two of them simultaneously and got a length of each vector, I noticed that as I point out, there will actually F2 is double F1. Why? Because F1 looks to be 2 centimeters long, F2 looks to be 4 centimeters long. So the magnitude of force F2, or how much oomph I'm giving to force F2, is twice as much push as F1. But based on the tips of their arrows, they are acting in exactly the same direction. Okay, so then what you can do is you can combine these vectors by placing them very simply, or simply by adding them together. So this is either called a net vector or a resultant vector. So again, if I have, I'm sorry, I thought I did it on this slide, but I don't. So let me just see if I'm saying anything important here. Okay, to add the vectors together, they must first represent the same physical quantity, meaning you can't add an acceleration vector to a force vector. You can't add a velocity vector to an acceleration vector, okay? You can't do things like that. You can only add velocity vectors to velocity vectors. You can only add force vectors to force vectors. Okay, so you can qualitatively add them in a graphical fashion, or you can do it using geometry rules. We're only going to do it first way. So one of the things that you'll see on my next little set of exercises that I have you do is I will have you qualitatively combine a few vectors. So over the course of the next several slides, let's look at some examples of putting together these vector type quantities. Okay, so I'm going to first talk about collinear vectors. And what it means to be collinear, quite simply, is that they're parallel, or they're pointing in the same direction, okay? So when I have a collinear vector, they're acting the same way. So going back to my analogy of when you and your buddies ran out of gas, this would mean both of your buddies went to the trunk of the car, and both of your buddies are pushing from the trunk of your car. They would be acting collinear in the same direction when they are pushing from the trunk of the car. So if they point in the same direction, all you need to do is connect them tip to tail, and in any order you desire. You can put 1 first, then 2 second, 2 first, and then 1 second, it doesn't matter. And when you combine them, the net or resultant vector is just from the beginning tail to the ending tip. So that's a lot of words. Let's see what I mean here. I take F1 and lay it down, and since F2 is in the same direction, I lay it down so that the tail of F2 lines up to the tip of F1. Then the resultant or net vector is simply measured from the beginning to the end. Okay, so what this means is if one of your buddies is pushing from the rear of the car and your other buddy joins in and pushes just as hard from the rear of the car, it's as if, as your mom and them would guess, one person is pushing twice as hard as 2 people pushing with individual forces. So when they are collinear and acting in the same direction, you just simply combine their actions to get the net value. Okay, so if we were to measure these things, remember F2 is 3 times, I'm sorry, scratch that. Going back 2 slides ago, and maybe I'll do that real quick. I'm adding my F1 and F2 from this picture. And if you can see from the ruler laid on this picture, F1 is about 2 centimeters in length, F2 is about 4 centimeters in length, and that means that F2 is double F1. Now, what does that mean? If this is force in newtons, if F1 is 10 newtons, F2 is 20 newtons. If F1 is 1,000 newtons, F2 is 2,000 newtons. I'm not sure exactly what scale it is, but what I know for sure is that F2 is double whatever number is assigned to F1. So now going back to my other slide where I added these together, F net has a length of one, we call F1 1 unit, F2 2 units. There's 3 total units of length in F net compared to F1 and F2. So in other words, if F1 is 10 newtons of force, F2 is 20 newtons of force, F net is 30 newtons of force. It's the sum of the actions of the two. I don't think that is very difficult for us to interpret. Okay, now, what if they are anti-parallel vectors? Anti-parallel vectors act in opposite directions, and then quite simply, what you do is instead of combining them, well, you still technically would combine them tip to tail, technically. You still would do something of that type, but now I'm taking the difference between them. So I'm going to do this so that F net is what is left over. I subtract the magnitude of F1 away from the total magnitude of F2. Now, since F2 was double the original magnitude of F1, that means F2 wins. And I'm sure that doesn't surprise anybody. If you're pushing twice as hard as your buddy from the opposite way, the object that's being pushed is going to move the way you're pushing it. However, because your buddy is pushing opposite of you, the action you're supplying will not totally transfer to the object. As a matter of fact, you're wasting half of your pushing because your buddy is pushing in the opposite direction, which is canceling your action. So if the vectors are collinear or lie in exactly the same direction, but are anti-parallel, then you subtract them. And the direction of the winning vector is in the direction of the one of the greatest magnitude. Okay, so let's just look at an example of combining these 3 vectors together. 3 people are pushing. Somebody's pushing with 8 newtons, somebody's pushing with 12 newtons, somebody's pushing with 20 newtons. The length of these vectors in some way is representing their individual magnitudes. The 8 Newton vector is the smallest, the 20 Newton vector is the biggest in the picture. Now, if they all are working together, I would literally just combine them. Oh, I'm sorry. What am I doing? Let me back up. I apologize entirely. Let's start like this. Sorry, I messed up. I didn't add 3 vectors. I added 2 vectors. Sorry. I am adding an 8 Newton vector to a 12 Newton vector. I don't have my spectacles on. That's how poor my vision is. Now I can see that I was adding 2 vectors, not 3. So I'm supposed to find the sum of F1 and F2. They are collinear, meaning pointing in the same direction. They are parallel. Okay, so that means all I need to do is combine them together and add their magnitudes so that F net would be 20 newtons. The third one was not to be added to the first 2. The third one was the result of the addition of the first 2. Sorry about my lack of paying attention to what I'm doing. So again, combining the first 2 vectors gives me the net vector, F net of 20 newtons. Now let's see this next example that I'm going to do. I'm going to combine 3 vectors this time. F1, F2, and F3. Okay, now F1 and F2 are acting parallel in the same direction. They can combine together. F3 is collinear, but it is anti-parallel to F1 and F2. It is in the opposite direction. And I think we can envision F3 is canceling what F1 and F2 are trying to do. Now, I hope you can notice that if I add F1 and F2, I get a total of 50 newtons of action. And in the opposite direction to the 50 newtons of action of F1 and F2 is an uphill push of 40 newtons. So the 40 newtons of F3 will cancel against the sum of the 50 newtons of F1 and F2. So the net action of, that's not right. I don't like my answer, folks. Why don't I like my answer? And I apologize that my answer is not right here. I made these slides and I obviously wasn't paying attention. Let's look at this closely and let's make sure we're clear. F1 and F2 are a total of 50. F3 is only 40 in the other direction. F1 and F2 win. There's 50 newtons pushing diagonally downward. There is 40 newtons pushing diagonally upward. So I apologize vehemently. I'm sorry, my arrow, the magnitude of it is correct. It is 10 newtons, but the direction of it is completely opposite. It should be pointing diagonally downward because the sum of F1 and F2 is greater than the upward push of F3. Sorry. This is what happens when I work without a net. So I hope everybody is clear on that one example. I messed that up personally because I do these things on my own and then I don't pay close enough attention. So we got that, I hope, in our minds that we add the two together, working together. They beat the one working in the opposite direction. So there's more push downward than there is push upward. Oh, that's great, Bill. Okay, so let's look at what happens and what we can do when they're non-collinear, meaning they're not pointing in the same direction. Like what happens when you're driving your car down the road and the wind is striking the side of your car. Now, let me back that up a minute. If you are driving your car and the wind's coming from behind you, guess what? Your car is going to be moving faster than you think. You can actually save a little bit of gas because the car gets pushed not only by the gasoline burning and turning the wheels, but the car is getting pushed by the wind. So these vectors will act together when the wind is behind your direction of action. What happens when you try to drive into the wind or run into the wind? I think we all know the answer to that. It's much more difficult. The wind is going to cancel against your direction of motion. But now let's consider what occurs if the wind is coming from the side of the car. As you're trying to drive north and south, the wind is blowing east and west. Well, these vectors of action still need to be combined. And really, it's not that difficult for us to combine them. What you do is, again, you do the tip to tail trick, and you look at which direction the net vector will travel based on the tip to tail connections. Okay, so each consecutive vector is placed tail to head, and the resultant vector begins at the first and ends at the final. So here's what I mean. Oh, okay. Then the magnitude of the vector has something to do with the length of the resultant. So maybe the words here don't do justice to what I'm going to show you to do. Okay, the last statement is saying that if you are real clever with geometry, you can get it exactly. The next to the last statement is saying from the picture, you can get an idea of the magnitude. The bottom thing says use your geometry rules for sines and cosines, and you could get the actual value. We're not going to do that. We're only going to do the third line down. We're going to draw the picture and look at the length of the arrow and estimate how much magnitude a vector has. So here's what I mean. Let's take these two vectors, F1 and F2. They are not collinear, meaning they don't lie in exactly the same direction. But what I'm claiming to you is I can still combine F1 to F2. How do you do it? Well, you just transcribe them and put them together. So down at the very bottom of the screen, I copied F1. And I copy it not only in length, I copy it in exact direction that it's going. Then I go to the tip of F1 and I lay on it the tail of F2. So notice I lay them tip to tail just like I did before. But now their tips and tails are not collinear, they're in opposite directions. So how do you find F net? Quite simply, you start at the beginning and you start at the beginning tail and go to the ending tip. And this is how those two vectors would combine. So if you have two people pushing, one pushing in direction F1 with an amount of push kind of proportional to its length, you have a person pushing in direction F2 with a magnitude of its push proportional to the length of F2. The action of the two of them on the same object would end the object heading in the direction you see by F net. Now, what else I want to point out here is I did my vector sum by starting with F1 and then adding to it F2. You will get the same result if you start with F2. So now I'm laying F2 out. I go, and then I put on the tip of F2, I attach the tail of F1. Now I start this net vector from the tail of F2, and I go to the tip of F1, and notice it's displaced sideways, yes, but its length is the same as the original F net, and the angle that it's making on the screen is the same as the original F net. So the point you get from this particular exercise is the order does not matter. All you will need to do is line the tails and the tips up, and you'll get the net direction of push or pull that a force will exert on an object. So what you can imagine is eventually when we go to our second test, unit 2 part, that I'm going to have you do on Moodle, I'll have some pictures of these kinds of arrows, and then I'll say which of these possible choices is most likely the net or resultant push or pull from combining those shown arrows. So here's just another example of doing that. Let's suppose I have these 3 vectors and I'm supposed to add them. Again, all I will do is I'll start with, sorry, there were 4 of them. Oops. I will start with F1 and I just put it randomly on the paper. I can attach 3 or 4 to it and then, or whichever one I want. It doesn't matter which order you do them in, but I'm probably my animation is going to do F2 next. Now, if only F1 and F2 were acting, I could find F net from F1 and F2 by simply just connecting F1 tail to F2 tip. And that would be the direction of F net from F1 and F2. Now, in actuality, if I then use F net from those two and combine it with the other ones, I have to get the correct result for the combination of all 4 anyways. I can combine them 2 at a time and then combine those results, and I would still get the right answer. But rather than do that, when I get to the tip of F2, I'm now going to lay F3 onto it. And unfortunately, it's behind my button, but I put the tail of F3 onto the tip of F2. Now I'm going to put the tail of F4 onto the tip of F3. And when I do so, it comes back around like so. Now I will go to the beginning of F1 and point an arrow in the direction to the tip of F4, and this will be F net, that combination of the 4 vectors. Now, just to make sure, here's just one more that we can play with. Again, I can do them in any order I want, but I'm going to take my V1, then I'm going to lay my V2 to the tail from the tip of V1. I'm going to lay the tail of V2, then I'm going to lay from the tip of V2. I'm going to lay the tail of V3. And then when I put those three together, I start at the beginning and go to the end. So this will be the net direction of the push of these three people acting together. All right, I am now done showing you the idea of using the vectors. Now, the whole point of this was to do it with regard to charge. So now we're going to use the concept of vectors to help us describe the pushing and pulling of charged matter. So we spent a good 40 minutes there discussing these ideas. Now let's apply them in the way that we want to apply them. Now, what I'm going to do is many times over tell the story of gravity as I tell the story of electric charge. And the reason I do this is that the formulation of the push and pull of gravity, actually I should be more specific, the formulation of the pull of gravity is very similar to the formulation of the pull of electricity. But it turns out pull of electricity has one important difference. It's not just a pull. Electricity has a push or a pull. Now the equations describing the behaviors are incredibly similar. But the weirdness of the actual behavior is dramatically different because charges can actually push or pull. Gravity, as I think we're all aware, only does one, and I'm going to call it a pull. We get pulled by gravity. We don't get pushed away by gravity. We're always going to get pulled to a massive object. So that is the distinct difference, but I do want to point out some of the unique qualities of gravity compared to the unique qualities of electricity and electrical charge attraction. Okay, now let me warn you, on the next few slides, there are a few formulas. Please do not panic. I'm not about the numbers so much here. We play a little bit. We dabble a little bit in numbers, a little bit. If I wanted you to have fancy calculators and put a bunch of numbers into crazy formulas, then I would tell you to take one of the higher level science classes. We offer those classes, we offer this same class at 3 different levels. So the level we're doing it at, I say we are doing it in a sense that we're getting the flavor and the concepts of what we're doing. We're not delving deeply into the numerics of it. Having said that, though, I'm showing the formulas and describing some things about the numbers simply because I think it's relevant to what we're trying to do. But again, do not panic. I'm not going to have you doing crazy formulas. I'm not going to have you doing crazy calculations. I don't think that's what we're here for. Okay, so gravitational force, I think we know, was discovered, or not discovered, it was described by Newton. I hate to use the word discovered gravity. It's kind of hard to say you discovered gravity because gravity was always there, and a lot of other people observed it. A lot of other people kind of had an understanding, of course, that gravity pulled things to the earth. It was just that Newton was able to generalize the description of gravity not only to what he encountered on Earth, but he was able to generalize it to the entire universe. Now, it turns out, though, he was not quite all the way right. It was kind of like Rutherford fixed up Thomson's model, but Thomson's model was the plum pudding wasn't quite right. So Rutherford made the planetary one. Well, it turned out that wasn't right, so they had to fix it up again. Well, Newton came up with the idea of gravitational attraction for the universe. It was mostly right, but when weird things weren't fitting, into Newton's rules. Einstein came along 200 years later and put in the behavior of relativity and the gravitational behavior that leads to our understanding now of the crazy things like black holes and stuff like that. So Newton was almost right, just kind of like Rutherford was almost right, but it later had to be revised a little bit by Einstein. Now, I'm sure we have all heard the story, the legend of what Newton was doing when he came up with the concept of gravity, or at least his model of gravity. The concept was always there. Everybody saw the action of gravity, not just Newton. Of course, as the legend has it, he was sitting under an apple tree. I'm sure you all heard this. And an apple falls from the tree, and magically he comes up with the idea of the story of gravity. Now, I emailed him and he didn't respond, so I don't know if that's true. So I don't really know if he was really sitting under an apple tree and envisioning how gravity worked. I don't know that. But I will point out one thing that the story kind of tells, if that story is true. It speaks of the nature of the day. Now you got to realize that Newton probably did this in probably 1700 or so. He probably came up with this idea. You notice Newton lived a long time. He lived a lengthy life. As a matter of fact, I think maybe, again, my date might be a little off there, but I don't think he died when he was 105, but he might have died in his 90s for sure. So, but the point I'm making is that Newton was allegedly sitting under an apple tree, and when the apple fell, he came up with the idea of gravity. What that speaks to is the fact that Newton lived a life of privilege. Newton was not a typical person living in the 1700s. Newton was a person of position and title, and his family had lands, and this gave him the wherewithal to do things like concern himself with the nature of the universe. Most people in the 1700s were just worried about surviving. You got to remember, at the time of Newton was not only was the economics of life, the feudal systems were still in place. The people, there was a lot of repression of all sorts of different classes of people, and all that sorts of stuff like that went on at the time of Newton. The bubonic plague the Black Death was raging through Europe at the time of Newton. So people were really not so concerned with how the universe worked. They were very concerned with just staying alive. So again, what I'm getting at is that Newton had the back family support of money and stuff like that to just hang out. He had other people work his land, and he collected stuff from them, and this and that and other thing. So he had this position of power and money that allowed him to work in science. Now, I'm not going to get into the sociological or all that stuff about whether that's fair or anything like that. All I'm going to point out is that that's probably what went on for Newton. He didn't have to work like everybody else had to do. But we benefited from that now, because I'm going to tell you what, Newton figured out a lot of stuff. He figured out a lot of stuff, and he was mostly right about the things he figured out. And not only, of course, did Newton figure out the ideas of gravity, he also described his 3 laws of motion. And his 3 laws of motion boil down to saying a body in motion remains in motion unless acted on by force. That's the law of inertia. He said that the force applied to an object, the acceleration will cause an object to accelerate. So if you apply a force, if you push an object, you'll change its speed. And the change in speed that it undergoes is inversely proportional to the mass of the object. So if an object is twice as heavy and you push it, it will accelerate half as much. That's what he said. If it's 4 times as heavy and you give it the same push, it'll accelerate 1/4 as much. That's what he said, which turns out to be dead on. And lastly, what else he said was, for every action, there is equal and opposite reaction. So when there's somebody trying to push in this direction, it feels to my hand like somebody's pushing back in the opposite direction. When I lean on this wall and try to push this wall, it literally feels like the wall is pushing back at me. That's the law of action and reaction. And he was dead on right with that one too. Now again, he was almost right with gravity. And what he said about gravity is that 2 bodies exert a gravitational force upon one another that's directly proportional to their masses and inversely proportional to the square of the distance between them. Okay, now the important thing about this is, as it says up there, the universal law of gravitation. And when I mean this is the universal law of gravitation, I mean it applies to any objects in the universe. That's crazy. That's crazy. Newton never been anywhere else. He was on the planet Earth. He did see how gravity worked on Earth. But to make the claim that his rules that he was establishing here on Earth worked on the sun, worked on the moon, worked in the next solar system or the next galaxy over, that's a bold projection of what you're observing around you. So he came up with something that works across the entire universe, even though he only had his experience on the planet Earth to draw from. Pretty impressive. Now, if you put the statement that I make there into an equation, this is what the equation looks like. Now, again, are we going to put numbers into this equation? No. But what I will point out to you is that F is the force of gravity. Now, it doesn't tell the direction, it tells the magnitude of force. So this tells how much push or pull you're going to get. Now, as the statement above says, it's directly proportional to the mass of the objects, whether that's me attracted to you, whether it's me attracted to the Earth, whether it's the moon attracted to the Earth, whether it's the Earth attracted to the sun. You would put the mass of those objects as 1 and 2. Now then, R is the distance between the objects. And notice that it's proportional to the square of R. Now, how he came to this conclusion, it's not really clear to me how he ultimately came to the fact that you had to take R times R in the denominator as opposed to just R. Okay, now the interesting thing is we call this an inverse square law. An inverse square law means you divide by the thing, but you have to take it to the power 2. So then what is G? G is called the gravitational constant of the universe. It's a fudge factor that makes the 2 sides equal. So the left side isn't equal to the right side unless you multiply the masses divided by R squared by a magic number. Now this magic number is universal, meaning it doesn't care if M1 is you and M2 is me. It doesn't care if M1 is the Earth and M2 is me. It doesn't care if M1 is the sun and M2 is Earth. The same magic number G works for everything in the universe. And turns out this magic number has been measured. And it's a tiny little number. I think it's 6.67 times 10 to the minus 11. It's hiding behind my stop the meeting sign. But I'm pretty sure, because I'm such a geek, that I know what that number is. 2/3 times 10 to the minus 11. Now what you learn from that number G is that it is tiny. It's 10 to the minus 11. What does that mean? 0.0000000, 10 O's, 667. So what does that mean? If F is going to be of a sizable number, then M1 and M2 had better be big, because otherwise G is so small that there's not much gravitational pull. That's probably a good thing. Why? Because you and I have small m's compared to what we're talking about. So there's no appreciable gravitational pull between me and you. However, the Earth has an m that is 10 to the 24. That's a big number. So when you put for M2 a number like 10 to the 24, it's massive compared to that number for G. So there is, of course, a very large gravitational force, a pull that we feel due to the Earth yanking on us. Again, your mass and my mass put in that numerator with that tiny G number, we ain't pulling on each other at all. The Earth pulling on you, not because of me, but the Earth, because the Earth has a mass of 24 zeros, positive zeros, making that number huge, that there's a massive pull by the Earth on you. Okay, now, I just want to show you here a picture of the dude who figured out the value of G. There's the magic number. It's not hiding behind the sign anymore. It is, as I said, 6.67 times 10 to the minus 11. The universal gravitational constant is tiny. It was figured out in, I think, about he did the experiments in 1790, as it says, 1797 actually. Took him a year to figure this number out. So this guy figured this number out around 1797 or so. His name was Henry Cavendish. And this is a cartoon of his experiment and what he did. And this cartoon doesn't really do it justice. Here's the trick he did. He made a pendulum. Scratch that. He didn't make a pendulum. Sorry. He made a mobile. And if you don't know what I mean by a mobile, think of a baby crib. And the thing you suspend over a baby crib that hangs a bunch of little Peppa Pig characters or a bunch of different like unicorns or things like that. And it can move around and such. And the baby lays there and looks at it and feels good. So he made a mobile. But instead of putting little Peppa Pig figures or whatever else hanging from his mobile, he put huge rocks. And I'm not talking about little rocks. I'm talking about a couple tons. And he put one stationary ton rock, and then he put a suspended mobile ton rock. And believe it or not, there was enough pull that the mobile rock moved towards the stationary rock. And he could measure the torque, which is the turn that occurred. It took him, as you can see there, a couple years to do this exact enough to get enough pull from a ton rock onto another ton rock so that he could actually measure the value of G. So it was a very clever experiment, one of the hallmark experiments of the late 1700s. So this is the guy. Newton didn't figure out the value of G. This guy figured out the value of G. But then when you stick it into Newton's formula, everything works. Okay, well, let's talk a little bit about some of the properties of gravity. Now, again, really we want to talk mostly about charge, which we'll do on Monday of next week using a very similar formula. But some of these same properties of gravity apply to the properties of charge. So let's just mention a few of the behaviors of gravity and what results from objects being pulled upon one another based on their masses. There's the formula that, again, we're not going to worry so much about. There's a force on object 1 caused by 2. That's what that means. F12 is the force on object 1 caused by 2. And to figure out how much magnitude it has, you plug in the mass of 1, the mass of 2, and you divide by the square of the distance between 1 and 2. We call that R12 squared. That's the distance between mass 1 and mass 2. Now, here's just a cartoon showing, suppose I have two objects, object 1 and object 2, and I measure the distance between them. That will be this R12. And what we call this is a radial distance. It's the straight line between the two objects. So I will measure R as the straight line from one to the other. So it doesn't matter if I move object 2 circularly around object 1. Of course, the radius of the circle that I put object 2 on will be the same at any point on that circle. So when we say the radial distance, it's as if you're putting object 1 at the center of a circle and then object 2 on the perimeter of that circle. And you can move it around anywhere you want, and that radius would stay exactly the same. So that's what I say there. It is the radial distance. It's the straight line between the two objects. Okay, now F12, as I said, is the gravitational force on on 1 caused by 2. Now, if I reverse that, I could calculate F21. F21 is the gravitational force on object 2 caused by 1. Okay, so there's a number for how much pull object 1 gives to 2. There's a number for how much pull object 2 gives to 1. So now I put these two arrows in that are showing F12 and F21. F12 accounts for not only the magnitude of the force on object 1, it accounts for the direction. Notice it's pointing towards object 2, F12. Notice force F21 is pointing towards object 1. So what we would say is that object 1 is being pulled towards object 2. Object 2 is being pulled towards object 1. And that's the nature of gravity. It pulls objects to each other. Now, the other thing you should notice is that F12 and F21 are, well, I'm saying here they're radial forces because they act on the straight line between the two. But the other thing that we should note is that they are equal to one another. F12 equals F21. They have exactly the same magnitude. What is this saying? That the bigger object is pulled by the smaller object with exactly the same force that the smaller object is pulled to the bigger object. Okay, let me tell you what the ramifications of that are. This not only applies to those two objects, it applies to me, you, and the Earth. I am being attracted to the Earth, obviously. If I open this window on the second story here and jump out, guess what? I start accelerating to the surface of the Earth. So I am being pulled by a gravitational force to the surface of the Earth. What I'm claiming in this statement, the last statement at the bottom of the slide, is that the Earth feels a gravitational pull due to me. I pull the Earth. And I pull the Earth just as hard as the Earth pulls me. Now, the crazy thought about that is, how come the Earth doesn't come flying up to me? Why do I fall to the Earth? And it's quite a simple matter. Again, I will say that the pull that the Earth exerts on me is equal to the pull that I exert on the Earth. We pull exactly the same. But the difference is my mass is way different than the Earth mass. The acceleration that you take is F equals ma. So the acceleration is A equals F over M. So I have to divide the force by my mass to get my acceleration. Big pull on me divided by my tiny mass means big acceleration by me. Now let's turn to what the Earth does. Same pull the Earth feels. To find how the Earth will accelerate, you have to divide by the mass of the Earth. The Earth's mass is ridiculous. And when you divide the acceleration that the Earth experiences due to me pulling on it, you get essentially zero. So the Earth doesn't move towards me because it's so massive. I move towards the Earth because I'm so light compared to the Earth. So the acceleration is entirely experienced by the lighter object compared to the less light object. That's why it appears that the moon is going around the Earth. The moon and Earth are pulling each other equally. The Earth is so much more massive than the moon that the acceleration of the moon is way greater than the acceleration of the Earth, even though the forces of pull are the same. Likewise, the Earth and Sun pull each other equally hard towards each other. But the Sun is so much more massive than the Earth that the acceleration that the Sun experiences due to the Earth's pull is nothing. While the Earth's acceleration due to the Sun's pull keeps us spinning around the Sun. Okay, now I promise we're going to talk about charge and these same ideas, but that will have to be on Monday. Remember, I posted these slides if you would like. I posted our third part of test 1 that must be completed by Monday. This is coming up Monday. Make sure you complete the third part of test 1, the final 40 points of test 1 by 11:30 on Monday. Okay, so then I will see you next time. Peace out. Yes, yes.
Okay, so for the non-linear vector ones, how
Yes.
do you know which way like the arrow will go, like the point?
Well, okay, I will give you the arrows. So you just transcribe one exactly the way it is. So you just, so,
No, I'm talking about for the net chart, for the net one.
okay. So like say I have this added to this.
Mhm.
Okay, so I'm going to start, this is number 1, number 2. I'm going to go number 1. This is close to being right. And this is number 2.
And then number one's bigger, so then.
Well, it doesn't really matter. I just start at the beginning and I go to the end. Now, again, could do the same thing. I could start with number 2 and then add on to it number 1. Start at the beginning, go to the end, and this is the same net.
Okay, that makes more sense.
Okay.
Cool, thank you.